Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will begin our discussion of thermodynamics by discussing internal energy and enthalpy. Before we begin discussing these two topics, I want us to take a step back and try to get an overall purpose of why we are learning this specific topic in chemistry. And so I believe that purpose can be summarized through this cartoon drawing that I drew. On the left-hand side of the arrow, here we have this animated cartoonish looking ice cube, and it's currently melting. As it's melting, this ice cube is having this like mid-ice cube crisis where it's asking this philosophical question, why me? Why am I melting? And so we can go ahead and take this question to heart and just kind of broaden it just a little bit more and ask ourselves, why does an ice cube melt spontaneously when it's left outside of the freezer? Now, many of you guys might say that, oh, well, it's hotter outside of the freezer than inside the freezer, so that's why an ice cube melts. And that is true, but is there another underlying factor that drives an ice cube to spontaneously melt into its liquid form? And so we can go ahead and apply a similar question to reactions that you guys are familiar with, such as a precipitation reaction. Now on the left side of this drawing, here we have a solution that's filled with lead-2 ion. And on the right side, here we have a solution that's filled with iodide ion. When you mix these two solutions together, a precipitate of lead-2 iodide will spontaneously form. So very similar to the question that the ice cube posed, why does the mixture of lead-2 ion and iodide ion spontaneously produce this precipitate? Okay. What underlying factor enables the spontaneous formation of the precipitate to occur? And so overall, that is the main point of this chapter. So the goal, the purpose, is to understand why some reactions are spontaneous in the forward direction and why some reactions are non-spontaneous in the forward direction. And we can go ahead and take this statement and talk about the reverse direction. So why does some reverse reactions are spontaneous while other reverse reactions are non-spontaneous? And what we're going to do is we're going to understand that through the lens of thermodynamics. Okay, so let's begin. So what is thermodynamics? So thermodynamics, it's this very intimidating looking word. It just sounds intimidating. So let's go ahead and check out what its definition is. And so thermodynamics deals with heat and temperature and their relationship to energy, work, radiation, and properties of matter. And that's very important for us in terms of industry and engineering. And so, for example, if you were, the next future engineer that's trying to build this zero emission, all electrical gas vehicle, all electrical no gas vehicle, then you want to create an engine that would produce the maximum amount of work that's possible for little amount of energy that's consumed. And one way that you guys can assess the efficiency of that machine or any machines would be through a thermodynamic perspective. So if you guys are looking at the thermodynamics, the relationship of energy and work, we can gain some clues as to the efficiency of that machine and perhaps think about new ways to make that machine more efficient if it isn't efficient. So overall, the thermodynamics is governed by 4 laws, and it goes from 0 to 3. So 0, 1, 2, and 3. And each of these 4 laws that we'll discuss as this series of lectures progresses, it kind of gives us an insight into the thermodynamic process. It gives us like the quantitative assumptions that we need to understand the thermodynamic process of a chemical reaction. Okay. And so what is this thermodynamic process? Once again, we're stumbling on these terms that sounds really complex. So by looking at its definition, thermodynamic process is simply the passage of a system from one initial equilibrium state to another equilibrium state. And if it's not yet the final equilibrium state, then it's going to progress incrementally, if you will, until it reaches its final equilibrium state. And so an analogy to the idea of thermodynamic process would be you being inside your room playing like a video game or reading a book, or you're on your cell phone. And so just the idea of you performing one activity in your room. And if you guys do that for a extended period of time, then you're technically in the state of equilibrium. And so what would happen if your family member or significant other invites you to the kitchen to either eat lunch, dinner, try out a new cookie recipe, and the list kind of goes on. And so this invitation from your family member will kind of force you out of your equilibrium state. And you're going to go through this process to get to the kitchen. So you're going to meander your way somehow through the kitchen. And so that's what the passage of the system is referring to, right? This idea of going from one equilibrium state to the other, where in my analogy, the kitchen is technically the final equilibrium state. So that's when you guys are together in one room and you guys are eating that scrumptious cookie or that delicious meal. And so hopefully that analogy helps you understand what this definition is trying to convey. Okay, it's simply the passage of a system, and in terms of chemistry, it's the progress of a chemical reaction from one initial state to another initial state. One initial state to a final initial state. And so how can we understand the thermodynamic process that occurs? Now, going back to the analogy where you're in your room doing this singular activity and you're in this initial state of equilibrium, you can literally map out how you go from your room to the kitchen, right? And there's actually many ways that you can do so. And so you can go ahead and directly walk out of your room and walk directly into your kitchen. So that's like one path, one way to get to the kitchen. Another way is to, hop your way to the kitchen, or perhaps roll your way to the kitchen, or perhaps you guys are going to exit your room, use the restroom to wash your hands and whatnot, and then go to the kitchen. Or, finally, just for the heck of it, you guys can open your window. Hopefully you guys are in a one-story home. You guys can open your window, exit your room from your window, and enter through the front door to get to your kitchen. And so all of those different paths that I've described in this analogy, all of them are different with respect to each other. And the same occurs, the same idea holds when you guys are thinking about chemical reactions. And so, when a chemical reaction is being performed, what's difficult about it is that we can't really track all of these microtransactions that's occurring inside a solution. Okay. And so the microtransactions that I'm referring to in the analogy would be like all of the different paths that's possible for you to go from your room to the kitchen. And so for a chemical reaction, there's lots of microtransactions that's occurring in terms of energy and in terms of the conversion of one substance to another that it's really hard to keep track of. It's impossible to keep track of actually in a microscopic scale, just because we simply can't see it. And so one way that we can understand this thermodynamic process is simply saying, okay, well, screw understanding all the different microtransactions that's occurring inside this chemical reaction. Let's just focus on the initial equilibrium state and the final equilibrium state. And by comparing both the final and the initial equilibrium states, you get an overall understanding of the thermodynamic process that occurred in that chemical reaction. And so here, our main purpose is to be able to take the difference between the main purpose is for us to be able to take the difference of two states at equilibrium to gain a better understanding of the thermodynamic process. Okay, so that's like that's going from you in your room to that of the kitchen. And so for us to be able to understand the thermodynamic process, we need to have some type of like descriptors that's describing a specific perspective of the system at equilibrium. And so this is where state functions come in. So state functions are quantities or variables or descriptors that describe the state of a chemical, that describe the state of a system at equilibrium. And you guys have actually worked with state functions way before this chapter. So for example, actually a few examples are temperature, pressure, and volume. And so each of these items can act as descriptors that helps us view the progress of a thermodynamic process under different perspectives. And so when we're looking at a chemical reaction, and if we just wanted to understand the transfer of energy, for instance, then we can go ahead and look at temperature. And so if you take the temperature of a system before the reaction occurs, and if you take the temperature of the system after the reaction occurs, by taking the difference between the two, you gain an understanding of overall what happened during the course of the chemical reaction. We're not so much paying attention to the individual microtransactions that got us there. And so, for example, for temperature, if the initial temperature was 25 degrees Celsius, and if the final temperature is 35 degrees Celsius, there's numerous paths that can occur to go from 25 to 35. So for example, it can go from 25 to 26, then go back down to 25.5, then go to 27, then go back to 26, and so you have all these these different paths that can occur to get up to 35 degrees Celsius. However, we're not concerned with the path, so to speak. We're just concerned about the initial state and the outcome. And so we can go ahead and describe these items by using temperature, pressure, and volume, right? So we can describe the initial state of a system at equilibrium through the perspective of pressure. We can describe the initial final state of the system through the perspective of volume. Okay. And if you guys are taking the difference between the two states, then that's simply going to be things like delta T or delta P or delta V, which is once again something that you guys have encountered in prior chapters in this first year of general chemistry. Now, the state functions that we are going to look at, it's not so much temperature, pressure, and volume. We're going to look at internal energy, enthalpy, and entropy. And so these are new state functions that I'm introducing. And once again, these state functions serves as like a descriptor for a system that's at equilibrium. So we're looking at it we can look at it in terms of the perspective of internal energy, perspective of enthalpy, perspective of entropy. And we're going to understand how these other state functions will enable us to understand why some chemical reactions are spontaneous in the forward direction or the reverse, okay, or non-spontaneous in the forward direction or the reverse. Okay. All right, so with that said, let's go ahead and talk about the first law of thermodynamics. So the first law of thermodynamics tells us that when matter is not allowed to be exchanged between a system and its surrounding, only energy can be transferred. So let's go ahead and break down that first part of the first law of thermodynamics, because it's telling us a specific condition. And so when matter is not allowed to be exchanged between the system and its surroundings, then you guys have created a closed system. Okay. And so let's talk about open systems and closed systems real quick. If you guys are looking at yourself in a mirror, you see human body, human being, etc. And the one thing that human beings love to do is eat, right? And so because we're ingesting matter in the form of food, we are not closed systems, we are open systems. And we excrete matter through feces. Yep, that's right, we're going to poop. Talking about poop. And so we ingest food and we poop stuff out. And so because we exchange with our surroundings, both in energy and matter, we are open systems. Now, closed systems are systems that in which no matter is allowed to be transferred between the system and the surrounding. And so an example of this situation would be, placing a chemical inside your volumetric flask. So for example, we put a solution of A and B inside this volumetric flask, and then we cap it. And then the moment it's capped, we know that no physical substance, matter, can go in or out of this volumetric flask. And the only thing that can be exchanged is energy. Okay, and that's really important because it's going to enable us to calculate this one thing, and I'll talk about it in just a second. And so here in this case, once we've capped this volumetric flask, we have reactant A and reactant B inside this volumetric flask, and the only thing that can occur is the transfer of energy in and out of the system. Okay. And so energy is going to be transferred one way or the other, such that it's reached its final state where AB has been converted into product CD. Okay. And let me just complete the picture here. So all of this is capped. Okay, so no matter is being exchanged between the system and the surrounding. And the surrounding in this case is just everything that's around the volumetric flask. Now, the really cool thing about the first law of thermodynamics is that once we know that only energy can be transferred, then we can create some type of conclusion. And according to the first law of thermodynamics, the internal energy of the system can be calculated through the sum of the heat and the work performed. Okay. And so internal energy is going to be one of our descriptors, our state functions. And so we can understand a thermodynamic process through the lens of internal energy. And internal energy is the energy that's contained within the system. Okay? And so here, if we're looking at this volumetric flask, there's an X amount of internal energy that it started with. And when this reaction occurred, we can potentially get a different value of internal energy. And by comparing the internal energy before and after the reaction, we can gain some understanding of the thermodynamic process that occurred. Okay. So hopefully me repeating some of these things will help you kind of link these concepts together. Okay. All right. So once again, internal energy is simply just the energy contained within the system. And so notice how this term system is just so broad. You can actually apply this word system to anything that you can think of. So for example, the system can be your body. And so inside your body, you have all of these biochemical processes that's occurring. So we have like this anabolic and catabolic process that either converts energy into potential energy or potential energy to kinetic energy. And so the sum of everything that's happening within the system is going to be termed as the internal energy of that system. And so your system doesn't have to be a human body. It can be like the desk. Like your desk has an internal energy. And so when you're talking about molecules that make up your desk, so I'm just going to draw like a quick molecule here. And let's just say that these are desk molecules without going into the details of the composition of your desk. All of the energy, the internal energy for these molecules that make up your desk are stored in your covalent bonds, for instance. And so one can imagine that if you calculate the energy that's contained in the covalent bonds before and after the reaction, you get an understanding of the overall thermodynamic process that occurred. Okay. And so looking at its definition for the first law of thermodynamics, it's basically saying that the internal energy is equal to the sum of heat and work. And so we can go ahead and summarize that as delta U is equal to Q plus W, where delta U is the change in internal energy. And so once again, this delta, internal energy, not internal change, sorry. Okay. And so once again, this idea of taking the difference between initial and final state, delta U in this case, is giving us like a snapshot of the thermodynamic process that occurred in the course of the chemical reaction. And so Q should be a term that you guys are familiar with from the first semester of general chemistry. So Q is the symbol for heat, and heat is typically expressed in kilojoules or joules. Okay. Now, if you guys are talking about molar heat, then it's kilojoules or joules per mole, right? So it just really depends on the perspective of unit that you guys are trying to address. But long story short, energy units is involved in heat. And so work can be described as how energy was exchanged. And so if you guys are in a macroscopic perspective, one version of work is me pushing my laptop over the edge of my desk, and it'll, I don't know, do something. Or I guess that's a very odd example. But like, for example, pushing a boulder is an example of work that was performed in a macroscopic perspective. But in a microscopic perspective, when you're talking about a chemical reaction, a physical work can be performed. For example, if you guys have a combustion reaction, that combustion in the engine can like move a piston lid up or down, or not. Actually, it's going to move the piston lid higher up, right? So it's going to increase the volume. And then that can be coupled to perform physical work. But when you guys are talking about, chemical reactions that occur in lab, when you pour two solutions together, really there's no physical work that was linked to it. And so we can go ahead and imagine that the work would represent how the energy was exchanged or transferred in a sense. And so work, very similar to Q, it has a positive sign and a negative sign. And so if the value of your quote unquote work is positive, then that means that work was done on the system. Okay? And if you're talking about energy exchange, the system gained energy from the environment in the sense that work was done on it. And so if work is negative, then work was done by the system. Okay? In the perspective of energy exchange, that means the system is losing energy to the surroundings, and that's just a form of work. This idea of energy exchange. And so basically, when you guys are looking at this equation, this is telling you that the change in internal energy, delta U, can be summarized by the sum of Q and work. And so one can, if you guys think about one way how this equation works, let's just say that Q is representative of that total initial energy that you have, right? The variance of it would come from work, and so if you guys had like lost heat to the surroundings, then work was performed by the system, and therefore the value of Q would decrease, and that would produce, for example, like a negative value for delta U or something like that. And that negative value for delta U tells you that there was a net loss of internal energy when during the thermodynamic process, whatever it was. And so once again, the thermodynamic process, think about it like all those different paths to get to the kitchen, all of these microtransactions that's happening in the chemical reaction. All right. And so, that's only like one scenario. What I just described is just one scenario in which you guys can apply Q and W and be able to get some type of number for delta U. And it's on a case-by-case basis. So remember that Q can be negative, W can be negative, Q can be positive, W can be positive. And so just the interplay between the negative signs and the positive signs and their magnitudes, they each tell a different story when you guys add them together. But long story short, if there is a positive delta U, then overall it's telling you through that thermodynamic process, there was like a net gain of energy into the system. And if it's like a negative delta U, then overall there's a net loss of energy, net loss of energy from the system throughout the course of that chemical reaction or that thermodynamic process. All right, and so we're going to go ahead and take a look at work in terms of a chemical system, and we're going to go ahead and look at it under two perspectives. So electrical work can be performed by a chemical system. So if you guys can imagine, like your electrolytes, right? If you put like salt in water or something like that, that can conduct electricity. And so that's an example of electrical work. And we'll take a look at electrical work for chemical systems in the next chapter. But for what I want to discuss, I want to talk about pressure volume work. And so pressure volume work can be summarized as negative P delta V. And so because there's a negative sign here, we know that work is being performed by the system. Okay? And so if you guys might ask, well, wait, W should be negative if work is performed by the system. So if you guys performed algebra and moved the negative to the other side, negative W is equal to P delta V, right? So all I did is simply move the negative sign over to solve it specifically for W, right? And so here we're going to go ahead and take a look at two scenarios. We're going to look at the chemical system under constant pressure and under constant volume. And we're going to see how that's going to change the equation that's dictated by the first law of thermodynamics. All right, so let's go ahead and look at constant volume. So one scenario in chemistry in which a reaction can be performed under constant volume is a bomb calorimeter. And so a bomb calorimeter is, this really huge, clunky device. Feel free to, YouTube a video that will describe the pieces of the bomb calorimeter. It's actually pretty cool to watch. And so we can go ahead and summarize the main components of a bomb calorimeter. The bomb calorimeter is composed of like two metallic vessels, one on the outside and one on the inside. And so obviously we have the outer container, and that outer container is going to hold the water. And so there's going to be an inner metal cylinder, and that metal cylinder is what we're referring to as the bomb. Okay? And it's not like a grenade. It's not like something that you guys think about negatively in movies and news, et cetera, et cetera. And so this quote-unquote bomb is just a metal cylinder that contains a combustible substance, such as ethane or propane or some type of hydrocarbon. You can even put food in there as well to perform some food calorimetry in a bomb calorimeter. And so the idea is that you have this combustible substance that's inside this metal cylinder, and it's submerged in water. And once the fuse is lit, so to speak, a combustion reaction will occur inside the bomb. And because this bomb is a metallic cylinder, there is really no change in volume, right? So when the reaction occurs, the combustion could perform physical work through expansion of its container. But since this is a metal cylinder and since this is closed and encased, technically speaking, when the combustion reaction occurs, there is overall no change in volume of the container itself. So what does that do to our equation for the change in internal energy? So if you guys recall, delta U is equal to Q plus W, where W can be represented as negative P delta V. And so if we substitute that in, delta U is equal to Q plus P delta V. Yeah, I didn't put in the delta here. And so overall, the change in internal energy can be calculated by taking the sum of Q minus P times delta V. And so if this is the modification of our equation that was derived by the first law of thermodynamics, then we can plug this value in for delta V, and we'll see that this whole term is going to cancel out because anything times 0 is 0. And so overall, under constant volume, the equation boils down to the change of internal energy, the change in internal energy, which is describing, if you will, the thermodynamic process, the overall thermodynamic process. It can be summed up as simply Q, or heat. Okay. And so this is really cool because now we can understand, we can physically calculate the change in internal energy and get an understanding of the thermodynamic process if we can somehow calculate Q, or heat. So if we know how much heat was transferred from the system to the surrounding, and if we can calculate that using whatever. So if we can calculate that, then we can go ahead and determine the overall change in the internal energy of the system. Okay, and that's super powerful because now we're going from something that can be measured macroscopically to something that translates us understanding the thermodynamic process of what happened in that in the bomb calorimeter. Okay. And so the reason why I hesitated a little while ago and I said whatever was because we can. I didn't want to jump the ship real quick in terms of concept, but Q can be calculated from the product of mass times specific heat times a change in temperature, right? And this is something that you guys were introduced to in the first semester of general chemistry. Q equals to MCAT, or Q equals to cat. And so the cat would represent the specific heat, or I'm sorry, heat capacity. And the equations that you guys are going to use to calculate Q just really depends if you have specific heat as your given value or your heat capacity as your given value in more or less in a word problem setting. But overall, this is like super powerful because now we can go ahead and understand the thermodynamic process. We can go ahead and express the thermodynamic process in terms of internal energy of the system by simply calculating Q. Okay, and we can calculate Q by taking the difference in temperature. And remember, temperature is another state function. Okay. All right, so let's go ahead and look at constant pressure. So examples of reactions that occur under constant pressure would be things that you guys did in lab. And so in lab, you have like beakers, test tubes, the list of lab equipment can continue, but most of the chemical reactions that you guys are performing in solutions was mixed in a test tube or in a beaker. And that reaction is therefore exposed under constant pressure. Okay. And so the pressure that I'm referring to is atmospheric pressure. In this case, it's exposed to 1 atm. It's exposed to 1 atm if you're at sea level. The atmospheric pressure is going to change based on the altitude of where you're performing that chemical reaction. But regardless, if you're performing that chemical reaction at that specific altitude, it's still going to be under constant pressure. And so looking at our equation that was given to us by the first law of thermodynamics, we can see that the change in internal energy is equal to the sum of, and so I'm just going to go ahead and plug in minus P delta V into W. And so what I get is Q minus P delta V. And so since we're under a constant pressure, then none of these terms cancel out. And so if, let me just choose purple. So therefore, the change in internal energy can be calculated by determining the heat of the system. And you guys are going to take work into consideration, minus P delta V. And so this is a huge difference between under constant volume and under constant pressure. And so one way that you guys can calculate the change in internal energy under constant pressure is by determining Q and pressure and the change in volume. Okay. And that is a huge difference to this equation that we came up with for when the reaction is occurring under constant volume. Oops. Okay. And so what I want to, my main point for doing these derivations is that under constant volume, we can define heat as the change in internal energy. Okay, so we're kind of looking at it in reverse. However, under constant pressure, one way that we can define heat is by moving this term to the other side. And so therefore, heat under constant pressure is going to be delta U plus P delta V. All right, and so here in this case, notice that the definition for heat, Q, is different under different scenarios or under different conditions. And so we're going to go ahead and put a subscript here, QV, to represent constant volume, and QP to represent constant pressure. And so to not confuse the Q's, because, like whenever we say Q, it doesn't necessarily imply the condition. And so one way that we can separate the definitions between heat calculated under constant volume and heat calculated under constant pressure is by creating a new expression for QP. And so, for example, instead of saying QP is equal to delta U plus P delta V, we're going to represent QP as enthalpy. And so enthalpy can be abbreviated as H. And so therefore, enthalpy, or H, is equal to delta U, which is a change in internal energy, plus P delta V. And so we now have a definition of enthalpy, which is another state function. Okay. And so here in this case, enthalpy is defined as delta U plus P delta V. Enthalpy is abbreviated as H, And since H is a state function, or enthalpy is a state function, we can always understand the thermodynamic process by taking the difference of the enthalpy in the initial state and the final state. Okay, so